Hello everybody, I'm Matty Ice,
I'm L Money.
and we're going to be talking about physics. What physics is it's sort of the way that we can explain natural occurrence in the universe, and we often overlook physics in common day things, but it's very important, and we'll be explaining that later on.
We're going to be going over 5 basic topics in this video. The first one is normal force, then air resistance, and friction, momentum, and also the application of forces. And yeah, we'll be going into detail about them, explaining because certain people know the concept but don't understand how it's derived or what it basically means, and that's what this video is for. So the first topic that we're going to be going over is normal force. If you have two lines intersecting at a right angle, you have what's called a perpendicular. If you have two planes intersecting at a right angle, you have an orthogonal. If you have a line intersecting a plane at a right angle, you have what's called a normal line. And that's where the name normal force comes from. The definition of normal force is the reaction force of the surface on any object. Some factors of normal force are mass, gravity, and any force that's on the same direction. Non-factors of it would be volume and surface area. So now I will show 2 examples of how normal force is used. In this example, there's an object resting on a table, and there's the normal force acting upwards and the gravitational force plus an applied force being acted on the object going downward. Here, as you can see, is the formula. The summation of the forces is equal to ma. Now the object is at rest, so ma is equal to 0. So the equation would be normal force minus gravitational force minus the force applied. If you solve for normal force, Fn would be equal to mg plus the force applied. Basically, what this shows is that the forces acting on the surface are mg and force applied, because they're going downwards on the surface. So, since normal force is equal to the reaction force of the forces acting on the surface, Fn would be equal to mg plus force applied. Now, this is another application of normal force. As you can see in this free body diagram, the object is in free fall. So the only forces acting on it is gravitational force, mg. Now, when an object is in free fall, that means that there is no surface. If there is no surface, that means there's no forces acting on the surface, which means there can't be any reaction forces by the surface on an object, which means there is no normal force. This can be proven mathematically. Thanks to Newton's second law of motion, the summation of forces is equal to ma. Being applied to this problem, we have negative mg is equal to negative ma. It is important to notice that there actually is a downward acceleration on this object since it's in free fall, unlike the previous example shown earlier.
Now, let's talk about friction. Let's start with a situation. Alright? First, let's look at some things. So first, I have this brain quest thing, and we can notice that the height of this is much longer than the length of it and the width of it. Alright? So now, let's say I start pushing it while it's lying this way. Okay? I'm applying force to it, and there's a friction going against it. Now let's say I make it stand upright and there's less of it touching the table, and now I push it with the same force. Will its friction increase or decrease? This is a very weird question, and let's look deeper into this. Now let's look at this situation more in depth. Force of friction equals mu k or s, depending on the kind of friction we're talking about, multiplied by normal force. If there are no other forces in the same direction, normal force would be equal to mg. So mu k or s times mg. So, does friction increase if there is more contact area? The simple answer is no, and here's how we can tell one way. Recall that normal force, the factors of it are mass, gravity, and other forces. The non-factors are volume of the object, or the area of the surface that's being in contact with the other surface. So that's how we can prove it, because we know it's a non-factor, but how do we know it's a non-factor? Well, let's say it were lying down and this was much longer than this. We can cut both up into tiny slivers, where this length right here for both of them is 1 meter and this width is 3 meters. So that means the contact surface of each sliver is 3 meters squared. So we can tell right here this has more contact area, this has less contact area. But that doesn't matter because they both have the same total mass per meter squared. How can we tell? Well, you look. These slivers are much smaller in volume compared to these. So that means this must have more mass, right? Well, no, because there are more slivers of this. And because there are more slivers of this and less of this, that means this will have less mass per meter squared, but there's more of them, and that will be the same as this total mass per meter squared. So that means that normal force is not affected whatsoever based on its contact area. Normal force is the same here and here, and we know that this will not affect friction whatsoever because normal force is not affected by its area. And this holds true in any case. So we know right now area of the surface does not matter for friction.
What I have written down here is the equation for air resistance. Air resistance occurs when air molecules bounce off of an object's path of motion and slows it down. Air resistance occurs regardless of whether an object is going upwards, downwards, to the left, or to the right. To explain what each variable in here means, F of drag is, well, air resistance. C is the coefficient of drag. P is the density of the air molecules. A is the area of the object which is being affected by the air resistance. And V is the velocity. The reason why everything is negative is because air resistance is always going against the object's path of motion.
So remember that air resistance isn't just in the vertical direction, it is in any direction. So look here, this is Bob, he's all tired, he's running a marathon. Let's say there's some force that's allowing him to accelerate, and we'll call that the force of max. Opposing him in the same direction will be the force of drag, which is also known as air resistance. According to Newton's second law, the summation of forces is equivalent to the mass times the acceleration to max. So this would be the summation of forces, and this is how we would find Max's acceleration. Now we're going to be talking about the application of air resistance in the vertical direction. So let's just say something is falling. Well, when it's falling, here's what the forces will be. There will be a gravitational force, mg. There will be no normal force, recall, because there is no surface. And because there is no surface, there can't be a reaction force of the forces going against that surface. But because here we're talking about air resistance, there obviously has to be a force of drag going against mg. So let's look at this deeply. So Newton's second law of motion is the summation of forces equals mass times acceleration of the ball. The summation of forces will be the gravitational force minus the force of drag as displayed here, and that will equal mass times acceleration. So we know in kinematics that acceleration equals the change of velocity over the change in time. As velocity increases, that means acceleration will increase according to this. However, over here, as velocity increases, acceleration will increase and decrease. The reason acceleration will increase is because this right here, as we just explained, but the reason acceleration will decrease is because over here, as velocity increases, that means the summation of forces will be less. And we know that the mass of the ball is going to be constant. Because that's going to be constant, that means acceleration has to go down as the summation of forces also goes down. So how can acceleration go up and down at the same time? It's sort of like a paradox. But the thing is, while something is falling, it doesn't just continuously accelerate because of this. We know, due to this, that there's this such thing as terminal velocity. What terminal velocity is the maximum velocity something can be falling at, disregarding gravity or anything, because of air resistance. Since velocity here is squared, that means velocity will increase much more than acceleration will according to this. Well, because velocity is increasing a lot faster than acceleration, that means they could sort of catch up to each other and reach a sort of equilibrium. Because they're at that equilibrium, that means velocity and acceleration both will not increase or decrease at a certain point in time. And that is what terminal velocity is. Let's now talk about some doors. Doors are pretty cool. We often overlook their physics. So, let's ask a question about doors. Why is this better than this? You can notice in the picture the doorknob is farther from the hinges here than it is here. Well, this is how we can prove it. According to Newton's second law, the summation of forces equals mass times acceleration. And in this case, if we were opening that door, we would be applying a force to that door. And that would be equal to mass times acceleration. And because we know doors open in a circle, this would have circular motion and its acceleration would be v squared over r. So that can lead us to see that force applied equals mv squared all over r. And what does this say? This says that as r increases, the force that we apply on the door decreases, making this much easier to open than this. We've all had to keep the door open using an object of some sort, so why is this better than this? In this case, we have an object farther away from the hinges touching the door compared to this one where it's very close to the hinges. As we stated before, summation of forces equals mass times acceleration. There's going to be circular motion because door moves in a circle. So the summation of forces in this case would be the force of the door on the box minus mu k times mass of the box times g equaling the total mass of the system times v squared, v being the velocity of the total system, all over r. Well, we can think of the door having its own force on the box, and force equals mass times acceleration. So that means the mass of the door times the velocity of the door squared all over the radius of the door minus mu k times the mass of the box times gravity equals the mass of the whole system times the velocity of the whole system squared all over r. If we multiply radius on both sides, then we have the mass of the door times the velocity of the door squared minus mu k times the mass of the box times gravity times the radius equaling the mass of the whole system times the velocity of the whole system squared. And this, we know, as radius increases, then this will decrease. Because as radius increases, this value gets much bigger. And when this gets bigger, it's taking away from the force that the door is applying on the box. And this will eventually become zero when this equals this force, but this one is going the opposite direction. That's why it's much easier to keep a door open when putting the box farther away from the hinges than closer.
Now, to go over our final topic of momentum, here I have written down the equation for momentum. P is equal to mv, m being mass, v being velocity. Now, momentum can be involved in several different problems, such as elastic collision, inelastic collision, explosion. Momentum can also be within the system if there are multiple masses involved. Also, very important to take note of, momentum is always conserved.
Now let's look at the supervillain named Juggernaut. For those of you that don't know, he's a supervillain, and he's the supervillain of the X-Men. His power is that he is physically unstoppable once in motion. Another way to say this is that his momentum is very, very large. So we know that momentum equals mass times velocity. And we know that his momentum is very large. And we know that there are some other factors that go into this. So we're going to try and figure out how his momentum is unstoppable, what allows that. So overall, he's a big and slow guy. And because he's slow, that means his velocity is not that large. Also, we know that density equals mass over volume, so we can manipulate that to get mass equals density times volume. We can substitute this into the original momentum equation to get momentum equals density times volume times velocity. Again, his velocity is small, so that isn't the main part of his power. And his volume, well, he's a pretty big guy, but he's not that big enough to create unstoppable momentum. So that means that the only thing that could cause his powers is his density, which essentially means that the molecules that are sort of create him are very densely packed in comparison to other people. Also, some things we should remember: when he collides with things, he doesn't stop. We know that. So the summation of momentum equals the mass of Juggernaut times velocity of Juggernaut minus a mass of an object times velocity of an object, and so on. And we know that his mass is much greater than, that's what this symbol means, any other mass that he collides into. Whenever he collides into something, it's going to be an elastic collision. We know that his collisions would always be elastic, and that means that his energy would always be conserved in the system because it is elastic. Whenever he runs through a wall or something, the wall would break. So right now I want to talk about how that's even possible. According to Newton's third law of motion, every action has an equal and opposite reaction. Because of this, we would think that things wouldn't break because you can punch a wall and it wouldn't break, it would just apply a force back. But that's not necessarily true. Whenever you push on something or apply force to something, it would sort of bend a little. You can sort of think of everything as a spring. If you were to push on a wall, that wall would bend a little back because you're pushing on it. It would still apply the same force back on you, but it's being pushed a little back. So eventually, things will break when you push enough so the molecules inside the object get separated, and that would sort of be an explosion when it sort of abruptly breaks and there are pieces flying everywhere. This is because that the molecules don't have enough time to react. And because of this, the energy is still going to be conserved. If you're applying an energy, the energy is going to be conserved in the pieces that are flying everywhere. So now let's talk about the energy in terms of Juggernaut's collisions. We know that the kinetic energy of Juggernaut would equal the mass of Juggernaut times the velocity of Juggernaut squared all over 2. We also know that initial energy plus work equals final energy. So that means the mass of Juggernaut times the velocity of Juggernaut squared all over 2 minus anything that would get in his way, for example a tree or something, would equal the mass of Juggernaut times the final velocity of Juggernaut squared all over 2 plus those tiny bits and pieces of things that are flying around, displayed over here. So we already know that the mass of Juggernaut is a lot greater than any of these other things. So that means that to conserve all this energy, the velocity of those things will be very, very high. And we can tell this because the energy is going to be conserved since it is elastic. We can also relate this to momentum's conservation. The momentum of Juggernaut minus any other things getting in his way would equal his final momentum plus the momentum of the things that are flying because of him colliding with them. So essentially from this, we know that we should probably stay away from any debris whenever he's in the area breaking into things.
Alright guys, I just want to thank you for watching the video. I hope that the topics that we went over actually helped you in understanding new things and you actually learned something from them. Hopefully, after watching this video, you know why normal force is called normal force and where the value and magnitude of normal force comes from. I hope you understand why area of an object isn't a factor of friction. Also, why terminal velocity exists and why we should thank air resistance, since it's because of air resistance that rain doesn't kill us, since it falls from such a high altitude. And also why some superheroes or supervillains are really, really strong. Yeah. What can I say? Physics is such an amazing subject. You know, it deals with a lot of things. I really think most people, scratch that, everyone in the world should have a basic concept on physics, since it does affect everyday life. We just don't put thought into it. And yeah, this is me and Matthew, who isn't currently present with me, signing out. We hope you enjoyed the video and have a nice life.